Hello, everyone. So today I'll be talking about planning and learning in this ever restless bandits. And this is joint work with my supervisors, Eric Garage and Yusuri Adobiasai from HSA. So yeah, this is the outline of the talk. I'll talk briefly about the motivation of restless bandits. Then I'll describe the planning problem, the model and solution. We assume that some parameters of the problem are unknown, and I describe the learning problem. And after all, I describe the numerical analysis that I did for these two cases and conclude the talk afterward. Hi, Eric.
It's online.
Yes.
Okay.
So we have already seen this scene during COVID, where we have lots of patients and limited resources at hospital. This can be essentially an instance of restless bandits, where we have a number of arms or patients, and we have limited resources or nurses to assign to these arms. Different patients may have different disease, and different disease have different progression rate. So the question is that how should we assign our resources to the patient, or how we should schedule our resources in this hospital so that the efficiency is maximized. Such problem may appear in different applications. For example, we can have a situation of a human operator dealing with a set of robots in a factory. So the human operator cannot assign tasks to these robots at once. It can focus on only one of the robots, and then depending on the location of the robot, the task, and the path that is going through, it can decide which robot to assign or to monitor. Or this scenario may also happen in factories where the repairman, we have a crew of repairmen that we send out to to repair the machines, and not all of the machines can be monitored at once. So only a subset of them can be assigned to the crew or repairman. The question is that which subset of these machines should be assigned so that the cost of the factory, maintenance of the factory is minimized. And also it can apply for sensor scheduling in autonomous driving, or it can be data scheduling in cellular networks. So in all of these problems, we are interested in finding a policy such that the assignment or the allocation is optimized in these scenarios. So first of all, I'm talking about the planning problem, where we model the problem as a Markov decision process for restless bandits. We assume that we are in a finite discrete time horizon denoted by T. We assume that we have n available arms indexed by 1 to n, and we assume that each arm is an independent controlled Markov process. The state space for each arm is denoted by xi, and there is an index for the time as well. And the action that we choose for each arm is either 0 or 1. By 0 means that the arm is not allocated, and by 1, it means that the arm is allocated. Essentially, this can be extended to multiple actions or partial resource consumptions. But for the focus of our talk, we just limit to the two actions, which is the typical of the restless bandits and most of the works working only with a binary action in these setups. So for action 1, we call it active action. The transition matrix for the arm that is activated is assigned by PI1. And for action 0, we call it passive action, and it can have a different dynamics. And when we say that the Markov processes are independent, this means that the transition priorities for different actions and different arms are independent from each other. So allocating resources to one arm is not affecting the dynamics of the rest of the arms. And then we have a per step reward, which depends on the state of the arm, and the action chosen for the arm. And this is the linking assumption that we assume that only at most m of the arms can be activated. So here is a motivating example. Suppose that we are in this data scheduling network, and these arms can be these data queues, and the servers are the servers that we allocate arms to that. The number of servers are typically lower than the number of queues, and then we have to decide at each time which subset of these queues should be allocated to the servers. The state of each queue can be the length of the data in each queue, which can increase stochastically by these lambda rates. And once the queue is allocated to the server, then the state of the queue may decrease or deterministically decrease according to the rate mu. There are definitely costs for this system. We have the holding cost, and we have the serving cost. And the question is that how we should assign these queues to these servers such that the overall cost of the system is minimized. Or equivalently, we can say that the reward is maximized.
So here, when you say that the M arms can be activated at the same time, is it like it's like that?
Yes, at most M of them can be activated at the same time.
Okay.
Or yeah, they're essentially at the same time.
So for this kind of server problems, the action set
Sorry.
is that if the action 0 and 1 is indicating which server it is.
Yes, whether we allocate to a server or not.
Where
So
does not-
binary decision making for each.
where it does not indicate which server it is to assign.
Oh no. I mean, there are. I mean, you can have some logic or rules for that, but the structure of the problem that we are dealing with is that it's type of a binary action, whether we allocate or not. Because it's like you may have different nurses, you may have different patients. You decide whether to allocate a nurse to a patient or not. It's not like choosing which nurse to go there. So that can be a different problem or another level of problem.
So nurses could be allocated same nurse could be allocated at over a period of time according to in your model. It can happen
Yes.
that they are working for 5-10 periods.
But the thing is that we can have another rule for that to allocate which nurse to go where. But the thing is that whether it is a need to a nurse to be there or not.
Okay.
So we are solving that question.
Okay.
But which nurse to go, that can be a different problem.
Yeah.
So essentially, given the time horizon t, the number of arms as n, number of arms with these parameters that I defined earlier, and where at most m of them can be activated at a time, what is the policy that maximizes the expected total reward over all arms given the initial state? That's a typical objective function for restless bandits, but the restless bandits is not limited to finite horizon setups. This can be for discounted horizon setups or infinite horizon setups. But for this work, we focus on finite time horizon setups to the assumption that we are going to define later for risk awareness. So first of all, the problem suffers from curse of dimensionality, as the cardinality of the state space is exponential in the number of arms. If we have 100 patients, each with 3 states of disease, then the state space is huge, it's 3 to 100. And the cardinality of the action space is n choose I from 0 to n, because we can at most choose m of the arms. So that the computational complexity of the optimal policy by doing the backward induction would be exponential in the number of arms. So what Whittle did in 1988, it introduced a heuristic method to solve restless bandit problem, which we refer to that as Whittle index policy. And essentially what it does is that it tries to allocate a priority index to each state of each arm. And then at each time instance, we look at the indices and select the arms with the highest index values. So suppose that we have these 3 arms, each arm has 3 states. And suppose arm 1 is at the state 2, arm 2 is at the state 1, and arm 3 is at the state 3. So in this setup, if we want to select one arm, we select arm 3, which has the highest index. If we want to select two arms, we select arm 1 and arm 3 according to the indices values. So somehow we are in the limit of our budget, and we are not violating that. And this is a simple rule that we look at the indices and select the arms with the highest indices. I'll later describe how we can obtain these Whittle indices, but for now, I just want to have you the overall sketch of what this index policy does. And this approach introduced by Whittle reduces the computational complexity significantly. So now the computational complexity would be linear in the number of arms rather than to be exponential. So it decomposes the problem into subproblems, and we solve the Whittle indices for each arm separately. That's how the computational complexity would be linear in the number of arms. But the drawback of this approach is that there are certain conditions need to be satisfied, which we call them as indexability, that may not hold for all problems. And also, this approach is a heuristic and suboptimal in general. There are certain cases that this can be optimal, but very limited. So what we do for this in this work is that we assume that the risk neutrality assumption may not be suitable for all restless bandit problems. And we want to incorporate risk sensitivity at a level of the total reward generated by each arm, by all arms. And for that, we use the expected utility function, which is a commonly used notion used in the literature for risk-averse decision making. So we are the first to analyze a restless bandit problem with a risk-averse objective by using the utility function formulation. And this study has not been studied before analytically. So here we are trying to have different form of concave or convex utility function to have different risk-averse behavior, like risk-seeking or risk-averse behavior of the policy. So essentially, these are the three different type of risk utility function that we use in our numerical analysis. The first one is a simple rule, is that if the total reward is above some threshold, where in this case it's 0.5, we assume that we are good. We are hitting above the threshold, and we don't care about the exact reward value. As long as we are above the threshold, everything is good. And if we are below the threshold, we are not receiving any reward for that. But this hard rule can be a bit smooth. We can define an exponential function for hitting the threshold if you are below the threshold, and we can also do that for the whole total reward problem. So if we are in a risk neutral setup, then there would be a linear line. Here it would be a utility function, but as we introduce this curve, we are introducing risk averse and being risk sensitive toward our objective. And if we increase the order here, then we would reach to this space where we have an exact threshold to satisfy or not. So now this is the new problem that we are dealing with. Given the time horizon and a utility function for each arm, and given the arm parameters where at most m of them can be chosen, we want to find a policy which maximizes the expected utility function sum over all arms. And this is essentially the objective that we define, and it hasn't been studied in the literature before.
So to consider static risk measure.
Exactly.
So this model is allowing for, so in this model, you allow for per stage risk to be anything, you only care about the total risk.
Exactly. And
So if somebody has some kind of a coverage perspective in mind, then they might be critical about this kind of a measure. But if they only care about some coverage over a period of time, then this is fine, right?
yes,
This is-
so the thing is that you want to be risk aware with respect to the behavior of the whole system or the policy that you have, for example, for the hospital.
Yes, yes.
Or it could be that we could have being risk aware with respect to each patient separately.
Yes, yes.
But what we did here is that we are being risk aware for the overall policy of, let's say, the hospital.
That's it.
So how to compute the vital indices? Essentially, what we do is that in our problem, we have the objective to be the expected value of the utility, such that there is a hard constraint that the number of activations at each time step over all arms should be less than or equal to n, which is a hard rule. Instead of that, we replace the hard constraint with a soft version of that, where the expected number of activations average over the arm and the time horizon should be less than or equal to m. Then we have the new objective function. So this is the approximation that we do, a relaxation that we do for our problem. For now, let me use the capital V here instead of the objective function so that we have a more compact notation. And essentially now we want to solve the new problem. So what we can do is that I can bring the constraint now to the objective function by defining this Lagrangian multiplier. And then now, since summation is a linear operator, I can take it out of the expectation, and now I have a new problem to solve. Then I can decompose the problem, and then I can define this objective for each arm separately, where this is like the utility function of the total reward for the arm minus the penalty term of the summation over the action that I select in the time horizon. And this objective function, now the policy and the objective value is dependent on the lambda, which is the penalty term that I introduced for this case. So to simplify the problem a bit, just to give the formal definition of how vital indices are obtained, let's replace the utility function with a unity function, with the identity function. Then the objective is just the total reward minus the penalty term. I can just rearrange the terms so that I get the expected of the total of this new reward function. So I can define a new NDP where instead of working with the rewards, now I define a reward which is subtracted by the lambda term, the penalty term, and the action that I chose. So now this, since I decompose the problem is not suffering from curves of dimensionality. And the only change that I need to do in my NDP is that I should change the reward function. And then I can use the backward induction to find the optimal policy for each arm separately. And that policy depends on the term lambda. So next, I want to introduce what is the indexability and how I can get the vital indices. But before that, I want you to take a bit of time here and see the relation between the policy and the term lambda here. So suppose lambda is a very large negative value. If action is 0, the reward is not changing, but if action is 1, then the reward is increasing. So I prefer the system prefers to take action 1. If lambda is very small, is very negative, the policy tends to activate all of the arms. But if lambda goes to a very large value, then if I take action 0, the reward is not changing. But if I take action 1, the reward value becomes very small. And then I tend not to activate the arms. So lambda is like the penalty that you have to pay for activation. If it's less, you try to activate more. If it's high, you try to activate less. So you can have a sense that how the policy is changing with respect to lambda. So now let me define a passive set, which is the set of states where the policy takes passive action or action 0. The passive set depends on lambda. The policy is two-dimensional. It depends on the state and the time step that I'm in. And the policy is either 0 or 1. So if I call the passive set as the set of states that I take passive action, then if such a state is linearly increasing with the penalty lambda, the problem is indexable. And for an indexable arm, the Whittle index of a state x at time t for arm I is defined as the inch-point value of lambda such that the state and time becomes part of a passive set. So as I go from lambda from -infinity to +infinity, the passive set is growing because this is a penalty term that I have to pay for activating the arms. And there are a specific critical value of penalty where the state becomes part of a passive set. If that happens, then that penalty value is the Whittle index of that state at that time. So in another sense, I can say that the policy is indifferent between action 0 and 1 at the Whittle index. So if lambda is the Whittle index value of the state and time, then the policy is indifferent between taking action 0 and 1. They have the same value. So let me also go through this in this plot. So assume that lambda is going from a very large negative value to the positive value or small value to a high value. So as I said before, if lambda is -infinity or very small, then the policy tends to take active action at all the states. Suppose that I have 3 states. If lambda is very large, since it's a penalty that I have to pay for activation, the optimal policy would be not taking any action for any of the states. Now consider state 1. As I increase lambda from -infinity to +infinity, there is a point where the policy for state 1 changes from action 1 to action 0 and it remains the same. If I have this behavior in my policy, that there is just one single point where the policy changes from activation to passive and it remains the same as I change lambda, then the problem is indexable. And that point of lambda is the Whittle index of the state that the policy is changed for. Now, this happens for a state 2 at this point where the policy changes from activation to passive and it remains the same as I increase lambda and the state 3. So now to get the Whittle indices numerically, either I can do a brute force search over lambdas, just changing and seeing this behavior, changing the behavior of the policy and get these Whittle indices, or I can do a bisection search to get the Whittle indices of the problem. And then I can, after finding the policies, I can check whether I have this monotonicity in the passive set. As you can see, the passive set is empty here. It's a state 1, a state 1 and 2, a state 1 and 3. So the passive set is increasing over lambdas. Either I can prove this analytically, that the passive set is increasing with the policy, with the lambda, or I can do it numerically by binary search. Then I can compare these policies, and if I see this behavior, then the problem is indexable. And if I know the problem is indexable, there are other ways that we can find the Whittle indices, which is called by adaptive grid search, which is for now out of the scope of this talk.
I have a question. So
Yes.
here, I mean, I'm in deterministic control. This lambda would be, and if it is continuous time, this lambda would be the value, the derivative of the value function with respect to the state.
Exactly.
What is the interpretation in this case? That you have some interpretation on this lambda?
So it's like the interpretation somehow intuitively we can say that since it's a cost that you pay and you decide not to activate the arm, it's like the retirement cost some or reward for that. So whether you get this fixed reward of lambda or you decide to play the game and let the arm continue.
Okay, so it takes into account the future value.
Yes.
Okay, okay, and it's telling you how much you can gain in some way.
Yes, exactly.
When continue.
Yes. And essentially that's how we select arms in the vital indices. So in the vital index policy that you have different vital indices value and you go for the arms with the highest vital index. So there's more potential that they give you the future reward. Because the retirement penalty would be higher for better arms. And then this is now we're getting back to the problem of the interest, where now we have this utility function over the total reward. There is a work by Barley where they introduce a new augmented arm risk neutral MDP, which is equivalent to the risk aware MDP and can be solved by dynamic program. So similar to before, we have to define a new type of MDP to solve this problem. And the new MDP is like this. Now I introduce a new dimension to the state space, and the new dimension is denoted by S. And the dynamic and essentially it captures the reward we accumulated so far. So the dynamics of the new state space is essentially summing up the rewards that we have accumulated up to time t. And the reward that we get for this problem, so this is like the first step reward, and this is like the final reward that we get. So if we are at the end of the horizon, we compute the total reward that we accumulated so far and put it inside the utility function. But before that, we were just incurring this lambda term reward or cost because we have a minus sign there in our setup. And the state space is now the initial state space that we had before. And since at time 0, the total reward that we accumulated is 0, this is going to be our initial state. Now we have defined this new MDP, and we can solve it by backward induction to find the policies given fixed lambdas. And as I do a binary search over lambdas, I can find the vital indices for this new MDP and get the vital index values.
Do you have any requirement for the function? Does it need to be monotone or translation values?
No, as long as I recall, there is yeah, it should be monotone. Yes, it should be strictly increasing. Yeah, the only assumption would be that it should be increasing. And not strictly, it can be just increasing.
So you need increasing for your that vital index property, right?
Yes.
Because it requires monotonicity
Yes.
to get a point where you stop in some.
Exactly.
Who is the risk measure? It's just a function.
Yeah.
Yes.
It's no translation variable.
So someone can do it.
Yeah.
So in order to get some sufficient conditions for indexability of our problem, we found that if these conditions are satisfied for our problem parameters, then we have this monotonicity behavior in our policy with respect to the penalty term lambda, and so the problem becomes indexable. So if we have a state space which is ordered, and then the reward function is not decreasing in the state, we define this some of the probabilities toward the end of the state space is not decreasing with respect to the state or the action, or if it's super additive. And if the reward is independent of the action that we choose, it's only dependent on the state, then the problem is indexable. And then we can use other methods for finding the Whittle indices if we can show that the problem is indexable. So this is not a necessary condition, it's just a sufficient condition to prove that there exist cases where the problem is indexable. However, for any general problem, we can do the binary search and prove that whether the problem is indexable or not. And this is a definition for superadditivity, in case you're unfamiliar with. So a function f is called superadditive on a partially ordered set x and y. If x1 greater than x2, y1 greater than y2, we have increasing differences in the function. So if x1 is fixed, the difference between y1 and y2 would be larger than for larger x, the difference between y1 and y2. If we change x, the differences would be smaller. So the second part of my talk will be on how to optimize a risk-aware policy when the transition probabilities are unknown in restless bandits. Essentially, we are now in the same setup with the difference that the transition probabilities under activation and being passive is unknown to the agent or to the learner, but the rest of the problem parameters remain the same as before. So now this is new problem that we are dealing with. Given the time horizon t, the set of arms, and where we assume that the transitions are unknown and at most m of them can be activated, find the policy which minimizes the expected regrets. And here, the d is the same objective as before, is the sum over the utilities it should be the utility of the sum, sorry, of the total rewards. And we are comparing the performance of the optimal policy with the estimated policy or the learning policy over the k episodes that we are in the learning setup.
Why do you need the expectation outside the brackets?
Since here we are assuming that we are dealing with a Bayesian setup, and we have randomness on the policy that we choose. That's why we do an expectation over that.
So you consider the random parts.
Yes. So here we assume that the problem has an unknown parameters for each arm denoted by theta star, and where the set is a compact set, finite unbounded, and we assume that these theta star are independent from each other because we have independent transition probabilities for different arms, and the algorithm maintains a posterior distribution denoted by phi ik and the dynamics of each arm. Since we are in a discrete setup, we can define the posterior distribution to be the Dirichlet parameters where nitk x iai is that the number of times up to episode k up to time t of arm I that we have seen a state xi and ai, and the next one nitk xi ai xi twice is the number of times we have seen transitions from a state x to x plus by action A up to time t of episode k for arm I. So keeping track of this, we can have the estimation of we can form a distribution over the true transition probabilities by essentially these are the Dirichlet parameters that we have on our problem. Parameters that we have on our problem. So just to give you an idea of what I meant is that let's assume that the transition probabilities for different action 0 and action 1 to be like this, where if we are deciding to choose passive action, the arm either state is some probability P or goes to the worst state, assume that the states are sorted from the worst to the best. And if we don't activate any arm, the state remains the same. So this parameter will be unknown. And to have an estimation of these parameters, we can count the number of observations that we have seen these transitions and use those count to have a distribution over the true parameter. So here is the algorithm that we do for Thompson sampling in Restless bandits. We have a prior over our parameters. And we can assume that the prior is an uninformed distribution or uniform distribution over the two parameters, as we don't know. And we have the initial states. We have k number of round episodes. And within each episode, what we do is that we sample parameters from our distribution, and we compute the estimated risk-averse policy based on the sample value. And then for the finite time horizon, we apply the estimated risk-averse policy, and then we have observation here, and we use that observation to update our count-based distribution, and then update the policy accordingly and going to the next round. And essentially, updating the count-based distribution is essentially the same as following the Bayesian rule to update the posterior distribution. Okay, so I just give you a brief idea of how we compute the regret for our problem. So what essentially we do as the first step is that we find the differences between the true transition probabilities with respect to the estimated ones, and we bound this error, the expected value of this error for different time horizon and different episodes. And after that, we apply to the backward induction to compute the objective function and find the regret bound for our problem, where in our setup, the regret bound is quadratic with respect to the number of arms, and it's sublinear with respect to the number of episodes, k. And also it's linear with respect to the state space, where x bar is the maximum value of the number of the states that I have, and it's linear in the reward for the arms. So essentially, there are two things that are most important here in obtaining the regret bound. One is that the regret bound should be sublinear in the number of episodes, and also it's quadratic with respect to the number of arms, where if you were to use Thompson sampling for a general restless bandits without applying the Witter index approach or decomposition approach, this would have been exponential in the number of arms. This is what we did for this work.
So what's the difference between the neutral case and parallel case?
You can apply. Essentially, you can get the same regret bound or the same form of ordering for the regret bound for the risk neutral policy, and you can get it for the risk averse policy. So what we did was that we obtained this regret bound for the risk averse policy.
So the regret bound for the risk neutral case is the same as.
Yes.
It's
very simple.
Is there a hidden n+1 somewhere, like, or no? You augment the state, so there must be.
I augment the state, but the transitions of the augmented state space is deterministic, and it's not affecting the one here. But I'm not quite sure that would I get exactly the same terms as the one in the risk neutral case, but in terms of the orders that is being quadratic in the number of arms, linear in the reward, and the state space is the same, but there might be minor differences. Maybe the constants are a bit different. So finally, the numerical analysis. So we have two sets of simulations, one for the planning problem and one for the learning problem. In the planning scenario, since there is no literature on risk-aware restless bandit, what we did is that we assume that we have the risk-aware objective and we are comparing the risk-aware with index policy with the risk-neutral with index policy and show that the risk-aware policy is doing better with respect to the risk-aware objective. For the learning scenario, since we cannot compute the optimal policy, the regret is computed with respect to the risk-aware with index policy. So we have a true risk-aware with index policy, and we have the estimated risk-aware with index policy, and we compare the performance of these two. Here are different setups that we consider. The time horizon is set from 3 to 5. The size of the state space is chosen from 2 to 5. All arms are initialized at the best state. The number of arms are proportional to the state space. So the smallest problem that we have is that we have 6 arms with 2 states, and the largest one is that we have 25 arms with 5 states. And then the portion of arms that can be selected is chosen from this set. We have the utility function that I shown before. For all of them, we have the target value to reach, like the threshold that we have, which is set according to these values. And for the smooth one, we have the ordering. So the orders are, we assume that we have different orders, so the slopes and the curve would be different for different utility functions. In order to, so that the total reward between 0 and 1, we assume that the rewards are sorted from 0 to 1 over t. And then we have a set of structured transition protein matrices, and we assume that different arms have different parameters and they are non-homogeneous. So those combinations resulted into 144 different setups, where we can see the distribution of the improvement in the risk-aware objective. So essentially, this distribution shows that how much improvement can we get if we use a risk-aware Whittle index with respect to the risk-neutral Whittle index. And essentially, on average, there is a 11.4% improvement in the performance with respect to the risk-aware objective. And it's ranged from negative 8% to 55% for some problem instances. So we are not comparing the optimal policy here. That's why, since we are doing a kind of risk-aware policy on heuristic, there are cases where the heuristic is not doing good with respect to the original problem. Now, just take one problem instance. For that problem instance, the total reward is shown on the right. And for this problem, we assume that we have a threshold set at 0.5. And as you can see here, there is more mass toward hitting the threshold rather than doing the risk neutral case. So the statistics are given here. If we do a risk-aware policy, 97% of the mass are above the threshold, while this is lower for the risk neutral case. But the thing is that once you have a risk-aware policy, with respect to the risk objective, you are doing better. But if you compare with respect to the average reward, we are doing a bit worse. So in the risk-aware objective, the average reward that we get is 0.6, while this is 0.7 for the risk neutral case. And essentially, it's the same for the whole problem, that on average, we are losing 3% on the average reward, but we are doing much better, let's say 10% or 11% better in the risk objective. For the learning scenarios, we consider different models. Stuff problems are based on the structured transition properties that we had before. We also got this model from a medical paper where we had different arms representing different patients suffering from advanced breast cancer. And the paper defined these 4 states. Since we need to order the state space, we define it to be like this, from 0 to 3. And there were 2 treatment options. which can be action 0 or action 1. Then we can assume that there is limited resources in the hospital so that we can apply the second action. So the problem can be modeled as restless bandits. And we essentially assume that the rewards are also increasing with respect to the state space. And here are the results for the regret. So essentially, we expect regret to be sublinear with respect to the number of episodes, as you can see in this problem. So if the regret can be a constant toward the end, this means that we can learn the baseline policy, which can be either the Witten index policy or the optimal policy. And for a special case of this problem, we might have some decrease in the total regret. This means that the learning policy is doing better than the baseline policy. And the reason behind that is that the baseline policy is not the optimal policy. So it might happen in the learning the parameters, we might do better than the baseline policy that we are comparing with. But essentially, we expect that if we divide the regret by the number of episodes, this should go to 0. So this means that we are learning a good baseline or a good policy for our problem as we increase the number of episodes. So for all these cases, we average over 100 sample path. So we have 500 episodes, average over 100 sample path, where each episode is a finite horizon time step with t equal to 5. Finally, what we did is that we introduced a risk-averse restless bandit problem. The only study which does risk-averse policies is the work done by Mate et al. In 2021, where they had a binary state partially observer MVP setup for restless bandits, where they modified the reward function to be fair or to be risk-averse in the numerical section. But what it is that we had a comprehensive analysis of the risk-averse objective for restless bandits. We provided a set of sufficient conditions under which the risk-averse restless bandit is indexable and how to compute the Witten indices. Also, we consider a learning problem where if the problem parameters are unknown, we can apply Thompson sampling to learn the risk-averse Witten index policy and have a regret bound which grows sublinearly in the number of episodes and quadratic in the number of arms. And finally, we show that we can do better than baseline and state-of-the-art works in the literature by following these approaches. Thank you so much for listening.